Hello, everyone, and welcome back to your channel of Math Made Easy. We are still working with Trig. Today, we are going to look at some relationships, like, first of all, Trig identities. So, what are the Trig? So, what are the Trig identities? And how do we, or where do we get them from? First of all, let's draw a very simple triangle, a right triangle with any angle, let's call it theta. And like what we did before, we are going to call that ABC, and the sides would be ABC. We know that sine of theta equals opposite over hypotenuse, and cosine of theta equals adjacent over hypotenuse. Okay? So if we take A over C and B over C, square them and add them up, meaning what is sine square theta? By the way, maybe I forgot to mention that. We usually write sine square theta, which means sine theta quantity square. The reason we don't write it sine theta square is that some students may erroneously write it like that. Sine theta, and then they say square, thinking that they are squaring the function. In fact, here they are squaring the angle, which doesn't make sense, right? There is no such thing as angle square, right? But nevertheless, instead, we could have said sine theta quantity square, but just to, reduce the confusion, if you forgot the parentheses or anything, we write it sine square theta. Maybe I should have mentioned that earlier. Well, I think this is the first time we mentioned the square anyway. So that's why we write it sine square theta to reduce confusion. Okay, so if I say sine square theta plus cosine square theta, let's write this. So this becomes a square over c square, meaning a over c quantity square, plus b over c quantity square. Meaning I can take a common denominator since it's the same. I can write this as a square plus b square. But what is a square plus b square? Yes. Pythagorean's theorem says that a square plus b square equals c square. So this is c square over c square equals 1. And this is the first identity. Sine square theta plus cosine square of theta equals 1 for all theta, whatever the angle is. Acute, obtuse, 90 degrees, 0 degrees, anything. Okay? Having said that, we can develop two more like artificial identities. It's the same identity, but it's like a corollary of that. If I divide the whole equation, say, by cosine square. So I can say sine square theta plus cosine square theta equals 1. I'm going to divide the left-hand side by cosine square theta and the right-hand side by cosine square theta. So I get sine square theta over cosine square theta is tan square theta plus cosine square theta over cosine square theta is 1. 1 over cosine is secant, so 1 over cosine square is secant square theta. So that is considered another identity, while in fact it's the same identity, but I divided by both sides by cosine square. Yeah, I hear you. I know, I know. I was going to do it now. What? Divide both sides by sine square, right? So we can write it like that, sine square theta over sine square theta, if you wish, plus cosine square theta over sine square theta equals 1 over sine square theta, right? Both, I divide everything by, so that becomes 1. Cosine over sine is cotan, square is cotan square, and 1 over sine is cosecant, so when you square it, you get cosecant square of theta. So even though they look like they are three identities, it's one and the same. You just divide by sine square once, by cosine square another time, and you get that. Okay? So these are, the three of them are considered trig identities. Since we mentioned that, how many of you remember how to prove that a squared plus b squared equals c squared? Unfortunately, the way it was taught at schools is that you draw a square here, and a square there, and then you divide this and you try to make equivalence of triangles, and it takes a while and you have to remember it. And if you leave it for a few years, you forget it and come back. It's horrible. It turns out that the 20th president of the United States, you know who's, don't Google it, don't Google it. You know who's the 20th president? James Garfield. He became president in the only palindrome year in the 19th century. You can read it right to left or left to right, like my daughter, she was born in 1991. So anyway, he was a lefty. I cannot write with my left hand. But in fact, he was ambidextrous. He could write with both hands. And there is an anecdote about him that he would entertain his visitors by answering their questions in writing. He said, wow, that's rude. Why wouldn't he talk to them? No, it wasn't rude. In fact, they loved it because he had the ability. And I don't know how, I don't even think it's possible, but it's said that he had this faculty that he could answer with both hands simultaneously, one hand in Latin and one hand in Greek. I don't know how, but it's crazy, mind-boggling. He was a mathematician and a lawyer. Oh my God. So I don't know, he will end up in heaven or hell. Sorry for whoever it has like the lawyer parents. Sorry, I didn't mean it. I know it's a bad joke, but we used to say it as engineers or mathematicians, usually engineers. Anyway, so what did he do? How he proved the Pythagorean theorem in a very neat and easy way. You don't have to construct anything, squares and whatever. You have a triangle. So let's try to make it like really good. So let's say this is 3, 4, 5. It doesn't matter. It does the sides are not important, but I just want to show you something. So here is a right triangle. He wanted to prove that the sum square. So if we say this is A, this is B, this is C, he took this triangle and turned it 90 degrees and slid it such that he brought the B here and the A there. So that stays 90 degrees. And he connected that. So that's, of course, would also be C, right? And this angle would be 90 degrees. You can prove that easily. I mean, you don't even have to spend much time to show that this angle is 90 degrees. And he said, okay, I have a figure here that we call, yes, a trapezoid. And the area of the trapezoid, as you learned, is the average of the two parallel sides, meaning you say A plus B over 2, and you multiply it by the height. Notice this is the height because it's 90 degrees. A plus B, meaning A plus B squared over 2. That's the area of this shape. And then he said, but guess what? It's the same as the area of three triangles. The first triangle is AB over 2. The second one is also AB over 2. And the third one is C squared over 2. He said, just for simplicity, let's multiply right and left by 2. Expanding the left-hand side, you get A squared plus twice AB plus B squared equals twice AB plus C squared. Yes, you subtract twice AB from both sides. He proved it. See how easy he did it? Amazing. Unfortunately, he was shot the same year he became president and died the same year. That's why 1881 is a very special case in American history. So you know, did you know now what event happened that never happened before or after since then? Meaning since then it didn't happen? Yeah. We had 3 presidents in the same year. The 19th president, he was president for 20 days, right? Until January 20th. And who's that? Huh? Rutherford Hayes, yes, was the 19th president. And after James Garfield died, of course, we had to appoint a new president, the 21st president, Chester Alan Arthur. So we had 3 presidents in the same year. It never happened since. Okay, now let's go back to business, okay? Enough history. I'm going to show you here. Should we do it now? Oh, I think we didn't spend much time. There are some relationships that help you, solve like trig equations and stuff. So let's write these properties here. If you add the sine of 2 angles, like angle A and angle B, so let's say sine A plus or minus B. Okay, meaning I'm going to write on the top sine A plus B and below it sine A minus B. It's sine A cosine B plus or minus, meaning if it's A plus B, you add. If it's A minus B, you subtract cosine A sine B. This is an important property. You can apply it to cosine. So if you do cosine A plus or minus B, you get cosine A cosine B. Notice when it's cosine, they are both cosine. When it's sine, you alternate. Minus plus, meaning if it's plus, you subtract. If it's minus, you add. Opposite to that, okay? Sine A, sine B. You can prove those easily, by the way. For example, let's take an example. Suppose this is A minus A, cosine A minus A. Okay, meaning cosine 0. We know cosine 0 is 1. But if this is A and this is A, you get cosine A times cosine A, which is cosine square A. Notice when I subtract, it's plus sine A times sine A is sine square A. So you get cosine square A plus sine square A, which is the same as sine square A plus cosine square A equals 1. So cosine 0 equals 1, and that's correct, of course. If you make A and B, you add them up and you make them 45 degrees, that would be cosine 90, which is 0, right? Cosine 90 is 0. So if we say this would be cosine square B, but if it's 45, it would be cosine square 45 minus sine square 45. We know that sine 45 equals cosine 45, so you get 0. You can repeat those for sine A plus or minus B. You make them 45 or whatever, and you should get the same result anyway. Okay, so that's the second one. The third one would be the tan. Tan A plus or minus B equals tan A plus or minus tan B. So if it's plus, you add. If it's minus, you subtract. divided by 1 minus plus. Notice the tan is sine over cosine. The sine, they match the cosine, they are the opposite. So the sine, they match the cosine. You can think of it like that or remember it like that. In the top, we match plus minus because it's sine over cosine. In the cosine here, we switch. So here we switch. Tan A times tan B. These are the three important equations. They are not identities. Like, well, you can think of them as identities. And here, in order to complete, and I'm going to stop there, what if A equals B and we use the positive? Well, you can use the positive or the negative, but if you use negative, you get sine 0, cosine 0, and tan 0. I don't want that. So if A equals B and you use the positive, so you say sine A plus A is sine twice A, becomes sine A cosine A plus cosine A sine A, which is the same thing. So you get twice sine A cosine A. You can check, for example, if A is, say, you can make it 30 or 45 or whatever. So if we say A equals 30, okay? A equals 30 degrees. Sine twice A is root 3 over 2, which is 2 sine 30, which is 1/2, cosine 30, which is root 3 over 2. Of course, 2 over 2 is 1, and you get the same answer. So how about cosine twice A? Well, here it comes in 3 different flavors. I don't know if you like vanilla or chocolate, but here are the flavors that we have. Cosine A, which is cosine square A. Notice when it's A plus A, you say minus sine A sine A, which is sine square A. So it's cosine square A minus sine square A. Or instead of sine square A, I can write it as 1 minus sine square A, right? So it would be 1 minus sine square A minus another sine square A. So it's 1 minus twice sine square of A. Or, like you expected, instead of sine square A, I'm going to write it as 1 minus cosine square A. There is a negative sign, so it would be 2 cosine square A minus 1. Okay? Finally, tan 2A. Notice that you can also, you can call that, okay, we're going to talk about that next time. I don't want to confuse you or make it hard. Okay, so here 10A plus 10A, right? Because I'm going to say 2A, twice A. So it's 10A plus 10A, or 2 tan A, divided by 1. And if it's plus, in the denominator, you subtract 10A times 10A, which is 10 square A. These also are very important relationships. Okay? So you don't need to memorize them, but as I said, usually it's like the multiplication table. You use it day in and day out, so eventually you would memorize them. Okay? So the more you solve questions or equations or solve equations like that have trig functions, eventually you would remember those. I learned this like when I was your age, maybe 50 years ago, and I never forgot them because I use them all the time. Okay, I think I will stop here. It was short lecture, but we covered many things. We proved the Pythagorean theorem using Garfield's method, and we had some neat stuff here, right? Okay, I hope you enjoyed it. Again, if you have any questions, please drop me a line, and I will get back to you as soon as I can. Thank you very much for watching and have a great day. Until we meet, have a great day. Bye.